Well, thanks, and sorry I wasn't able to make it in person. We've just gotten back this week from integration of Spider, so yeah, but I'll go ahead and speak today about cosmology from Planck and the search for inflationary V modes. Planck, of course, is a very large project. It's an ESA-led mission with substantial contributions from many other national agencies, including NASA. NASA contributed the focal plane technology to both the instruments that are on board Planck, the HFI and the LFI, as well as portions of the cryogenic. There are enormous numbers of people who contributed greatly to this project, and by no means am I taking credit for even a small fraction of it. But so just very briefly, there's too much cosmology from Planck to talk about in a 20-minute talk. So I'm going to take just even a very brief look at inflation from Planck and sort of where things are headed with the next generation of CMB polarimeters. So there are essentially several basic predictions, or if you don't like that term, observational probes that are somewhat generic to inflationary scenarios. And the ones that the Planck data touch on include these four: departures from scale invariant for the primordial fluctuations, limits on spatial curvature, departures from pure Gaussianity of the intensity fluctuation, CMB, and then of course limits on the tensor to scalar ratio that can be derived either from the contribution to the CMB, the unpolarized anisotropies, but also, of course, from the somewhat unique signature in the B mode polarization of the microwave background. So the data are these. This is a Planck Allsky CMB component map. So this is generated from a linear combination of the data at wavelengths longer than about a millimeter, and represents our best estimate of what the primordial CMB fluctuations look like on the full sky. Of course, the full sky maps don't do justice to the data set. Most of the activity that's happening down there is on scales that are below the pixel resolution in the full sky maps. So if you zoom in on a little patch that's roughly 25 degrees square, you can start to see some of the richness that there is in the data. And these, the data, of course, cover the full sky. It's not just isolated to a single portion of the sky. And the power of Planck to inform us about inflationary, our understanding of the inflationary epoch comes to a large degree at its dynamic range in angular scale, and its ability to reach all the way from the largest scales on the full sky down well into the silk damping tip. So that's really what distinguishes Planck from WMAP, of course, in addition to the increased sensitivity, is the angular resolution. So here I've just taken that same postage stamp of data and filtered it in angular scale to highlight the different physical effects that are going on in the primary CMB anisotropies. So the first column shows the large-scale fluctuations, the Sachs-Wolf region of the CMB plateau. These have been filtered, roughly speaking, on scales that are larger than about 1.5 degrees. And then on the middle row, or I'm sorry, the middle column are the acoustic oscillations. So these are the degree scale fluctuations in the CMB. And then the furthest to the right are everything beyond, roughly speaking, 20 arc minutes, on scales of less than 20 arc minutes. And then, of course, the first row are the WMAP data, and the lower row of data are Planck. And these particular data are the 143 gigahertz maps, but they're not quantitatively different than the 100 gigahertz data. So what you can see is that, of course, most of the power is on the larger scales, but then Planck has allowed us, and they're quite, certainly the signal to noise on the large-scale fluctuations are not limited by instrumental noise for either WMAP or Planck. And the same is true to a lesser degree of the degree scale fluctuation. But then really once you get into the damping tail, below the resolution that WMAP has any sensitivity, that's really where the new power of Planck to constrain inflationary models has come from. So you can, of course, quantify that in the power spectrum, and this is a plot from the paper 16 of the Planck release that shows the first of those inflationary probes, the broken scale invariance. So when one tries to fit a cosmological model which has been pegged to have a scale invariant primordial power spectrum, and you just compare that fit visually to a similar model, but you allow the parameter, the the NS parameter to float, the data clearly favor one which has reduced power on small scales, so broken scale invariance with a spectral index less than unity. So more quantitatively, what does that give us? Well, it gives us a measure of in sub s that gives us something less than unity at about 6 sigma, just really from statistical considerations. And that in and of itself is not a terribly new result from Planck. That was the WMAP data in prior experiments strongly favored these broken scale invariants in the CMB. What's probably most new from Planck in this regard is the robustness of that result, simple extensions or even not so simple extensions to the basic vanilla lambda CDM model. So this is just a smattering of where some of the largest degeneracies lie within sub S. So up in the upper left is the primordial helium abundance. On the upper right is the number of radiative degrees of freedom. Then there's a running of the spectral index in the lower left, and the tensor to scalar ratio in the bottom right. And for all of these, when you allow these simple extensions to the 6-parameter lambda CDM, the data have enough statistical power to usefully constrain these extended models. And even in that context, the broken scale invariance is quite robust. So the error bars on small scales are heavily impacted by foreground modeling. That probably, well, not probably, it certainly contributes more to the uncertainties on the small scales than statistical noise, or even relatively well understood systematics such as beam errors or time constants in the case of the HFI. However, the in sub S result is still robust to variations in that foreground model. The foregrounds are largely unpolarized, so you can expect improvements here when the polarization data are released. And that, of course, the next release is expected in the vicinity of March of the next year. With regard to spatial curvature, a number of things. Again, one thing that I won't talk about, but I'm sure you'll talk about this afternoon, are the impact of lensing on that have come from the Planck data. And one of those things that it's been able to do is to really confirm the flatness result when one considers a model that allows for spatial curvature. Just from the CMB alone, using the lensing data, you can constrain in the matter omega to lambda plane, you can constrain models quite closely to the flatness constraint, just using the CMB alone. And that constraint is very much tightened, as is shown in the right panel of this plot when you include the BAO data, the large scale. So again, another expectation from something like inflation is this flatness, and it's quite well constrained now just by the CMB alone. Another new thing from Planck is, of course, the Nongaussian ID, and you'll hear more about that this afternoon. I won't go into it in much detail. But again, the power comes from having essentially noiseless, high-resolution all-sky maps. Inflationary theories can, to some degree, be distinguished by the level of non-Gaussianity that they predict in the CMB. This is something one can observationally test. Again, but you might be concerned not only about statistical noise, but also, say, the contribution of non-Gaussianity from things like foreground emission. This is just another image showing both the all-sky map, the component map, as well as a couple postage stamps showing the 100 gigahertz, 143, and 217 gigahertz data in that same region of sky. Just to give you a feel for the level of the foregrounds in a relatively clean part of the sky off the galactic plane. And the broad frequency coverage of Planck has really been critical in understanding exactly what the contribution of the residual foreground contaminants is, not only to non-Gaussianity, but to the rest of the analysis. When you do the exercise, you find about the level of non-Gaussianity that one would expect given purely Gaussian primordial fluctuation. So I won't go into that in too much detail, but essentially, once you've subtracted off the induced non-Gaussian entities from late time effects. You find for this particular example is FNL local, a particular type of non-Gaussian entity, but for all of them, they're all consistent, essentially with purely Gaussian fluctuations. And the error bar on that statement that comes from Planck is significantly better than was had before. It has played a role in our ability to constrain some of those inflationary early universe models. Well, not just inflationary, some of the early universe theories. We're starting to get to the point where we can discriminate between different classes. These are just a couple examples of models that prior to the Planck result were not in any tension with data. And although we're not quite there yet, we're getting to the point where we're just from the non-Gaussian entity result, we can already start to limit some of these classes of theory. What, of course, we'd really like to get at is a direct observable, or as direct observable as we can, of the fingerprint of inflation in the early universe. And the holy grail there has been the E-mode power spectrum, so that we can get a probe to the tensor to scalar ratio. Planck has released limits on the tensor to scalar ratio based not on the B-mode polarization, but just on the temperature anisotropies. So this is just a plot showing the famous R versus NS plane that comes from the Planck paper 22. So on the abscissa is the N sub S result, and then the tensor to scalar limit that comes purely from temperature anisotropies on the large scale. The fluctuation power on large scales is shown on the y-axis. And Planck really hasn't statistically improved on either axis a great deal. But it's, like I mentioned before, especially the NS result is much more robust to extensions to the basic model. And so I think people believe it more, rightly or wrongly, than they did prior to Planck, the Planck release. And importantly, the data that we have are in extremely good agreement with both the BAO and small scale data. And all of that leads us to sort of look at a plot like this and start to distinguish between classes of theories that we think may or may not be viable with the data. This is, like I said, the limit in the tensor to scalar ratio is based purely on the temperature anisotropies, and that limit is essentially the best that one can do given sample variance on the amount of sky which is reasonably free of galactic emission. One may be doing a bit better than say WMAP, if only because it's been able to be a bit more aggressive in the amount of sky that's covered.
The conference has been muted.
Hello? I think that I've been muted. If that's not true, send me a text.
The conference has been muted. The conference has been muted. The conference has been muted.
Testing. Hello. Hello. Can you hear now? Hello.
After you connect, press *8.
Can you bring down the audio in here, please?
No, we're not sending anything out there.
Audio's out of control in here.
It's from the laptop out there, so.
All right, but in here.
Hello?
Yeah, you do that.
Hello?
Yeah, no, we can hear you.
speak while I can still be heard. I'll try to catch up. So the limits on R from Planck are, of course, coming from the temperature anisotropies, and the only way that we can hope to push down in this parameter space is to push down on direct observations of B-mode power to limit the tensor to scalar ratio. And given the results from the Nongaussian ID that seem to suggest that that the theory of the early universe that appears consistent with the data, at least consistent with the lack of non-Gaussian signatures, it makes this plot more meaningful, perhaps, than it was in the pre-Planck era. So how might we go about and do that? So here's a plot that shows what Planck might hope to do with regard to limiting the level of B-mode power on the CMB on the largest scales. So this is a plot that is, of course, showing in red the E-mode power spectrum, the sort of prosaic polarization that comes from scalar anisotropies, scalar quadrupole anisotropies at the surface of last scattering. And in blue are shown two different levels of tensor to scalar ratio, the power in the B-mode spectrum of the polarization of the microwave background, the odd parity states of the polarization in that in the linear polarization of the CMB. And what are shown there are for R of 0.3 and R of 0.01, which in these units, the limits from the temperature data alone are sort of in the middle of those two. And what are shown in the dashed lines are the sensitivity curves, the raw sensitivity curves from WMAP Planck, and then this is taken from the CMB pole emission study. And so EPIC, which is about as good as one could ever hope to do, is shown in black down the dashed line. The takeaway here is that the intersection of the Planck curve with an interesting level of B-mode power occurs only at the largest scales on multiples that are, of course, are below 10, or on scales that are larger than roughly 30 degrees on the sky. And this is a very difficult game. On those large scales, you're plagued most by foregrounds. Instrumental effects are significant. So this is going to be very difficult for Planck to probe this directly. And if it has any hope of doing it, it can only detect it via its measurement of the reionization bump in the B-mode power spectrum, again on the very largest scales. So while it's possible that Planck will put interesting direct limits on the B-mode power and therefore on the tensor to scalar ratio via polarization, it's likely that we'll have to wait for the current and the next generation of dedicated B-mode polarimeters to inform us about the level of B-mode power on the sky. So just to summarize real briefly where we are, from Planck essentially alone, what have we learned about inflation? Well, we have the departure from scale invariance to the primordial fluctuations, which are highly statistically significant and robust to single and several parameter extensions to the basic 6 lambda CDM models. They're robust to foreground modeling, and you might expect marginal improvements next spring from the polarization data. But it's not dramatically going to change the picture of where NS is at. In terms of departures from pure Gaussianity, there are, to date, the published values are derived only from the contribution to temperature anisotropies. It's a significant improvement over pre-Planck limits, and it's getting to the point where it's starting to distinguish between competing theories of the early universe. And we might expect modest improvements, maybe a factor of 2, when the polarization data are released. But again, it's not going to be an order of magnitude more powerful in this regard. And in terms of limits on the tensor to scalar ratio, the published values are derived only from the contribution to the temperature anisotropies that set a limit at about R of 0.11. And they are limited currently by sample variance of the roughly 20 or 30% of the sky that is most clean of foregrounds. And it's only a marginal improvement over pre-Planck limits. in principle, it can be improved upon with polarization data, but again, that's going to be a very difficult game to play, given that that Planck only has enough raw sensitivity to reach down to the highest angular scale, to the largest angular scales. So that's a summary for Planck, and just looking ahead, just very briefly, at the landscape for current and future experiments that are dedicated to this sort of thing. This is a compendium from the Quiet Collaboration published last year of the current best measurements of the E-mode power spectrum in the upper panel and then of the B-mode limits in the lower panel. The E-mode power spectrum is essentially in the same observational regime that the temperature power spectrum was in circa late 90s, where it's clearly been detected and fairly well characterized, but it's waiting for a definitive measurement. We hope that in March, Planck will publish that definitive measurement of the upper panel. And many of us are working on advancing the state of B-mode observations to a similar level. But we're not yet there. We're still at upper limits that are well above the upper limits that are set by temperature measurements. So you'll hear more about the small-scale experiments, I think, in the next talk. I'm only going to look real briefly at the large-scale measurements. These are where the ratio of the primordial B-mode power to astrophysical foregrounds, including the lensing, are largest. And so a number of experiments are focusing in the large angular scale regime. I've outlined those that are sensitive to those large scale modes on the left. So EVEX, Spider, and Piper are all suborbital experiments that are going after these scales, these large scales. EVEX extends, of course, the measurement down to smaller scales, roughly the same scales that Planck is sensitive to. Spider and Piper, on the other hand, are fundamentally large-scale machines with an angular resolution that is about half a degree. On the ground, there's BICEP 1 and 2 and now 3 coming online, as well as the Keck array and ABS, the Atacama B-mode search, and CLASS, the Hopkins experiment, also from the high plateau. Just real briefly, again, here's a line. This is a compendium of data, the BICEP Quiet Quad and WMAP data. It's a bit dated. I don't think it's the most recent Quiet data. And then cartoon drawing of the Planck theory sensitivity curve is shown. And then I've also just put on there corresponding sensitivity curves for Spider. The devil is in the details of how low in multiple you think these experiments can reach. You might be forgiven for thinking that Planck's going to make a many sigma detection of this for the shown level of tensor to scalar ratio, but again, it's a question of how close to reality the theory is of how well your instrument's going to work at those large scales. The same is true of Spider. We've extended it down to 10. Spider covers about 10% of the sky, and Planck covers the whole sky. Only about 10% of the southern hemisphere is worth observing for the purpose of doing B-mode work, simply because of the foreground contamination. But the point being that the next generation of experiments, those that are like Spider and Keck and CLASS and the other experiments that I've outlined, have the raw sensitivity to really push down and directly probe the B-mode power on scales where it peaks at around a degree, rather than relying solely on the reionization bump. So, what can we expect experimentally or observationally in the next sort of year to 3 years? Well, I think it's reasonable that we can push down in the tensor to scalar ratio from the experiments that we've discussed to below the 0.05 level, probably down to the 0.03 level. And I think that all of us expect that we'll be limited by foregrounds before we're going to be limited by raw sensitivity, at least for the first generation of experiments. Or at least we won't be able to definitively state that we are not limited by foreground B-mode contamination. I think that in the next few years, there is already considerable pressure on simple monomial potentials, and I think that we'll be able to make statements about them that are sort of at high energy physics levels of significance in the next few years. I'll just plug briefly, and then I'll happy to take questions if we can do that online. But I'll plug SPIDER briefly. We've just gotten back from our integration campaign in Texas, and the entire experiment's now shipped to Antarctica. It's a 4-emitter measuring, again, just on the large scale. So our angular resolution is about 0.5 degree, and we cover about 10% of the full sky. And we do it with roughly 2,500 live detectors, giving us a sensitivity that's about 5 times that of Planck. And this will allow us to probe inflation at a tensor-to-scalar ratio of about 0.03, which is really kind of probing down not only to the lift bound, but probably more fundamentally to the limit that we expect to be set by foreground emission, even in the most clean parts of the sky. And I'll just end real quickly. I know I'm behind, so I'll end real quickly with a movie of SPIDER this summer in Texas, if this works. It's up there in scanning. The experiments, at least for the suborbital experiments, they've gotten about as big as you can build them, given the constraints of the launch envelope. So if we're going to do better in the future, we need to be more clever about our multiplexing technology. But it's an exciting time, and I think the next few years we've got good hopes on reaching down to the limit of foregrounds, and I think that limit is likely to be around the level of a couple percent in tensor-to-scalar ratio. So I'll end there. Actually, I won't. I'll go on to one more slide. I want to just say 2 things real quickly. I indicated this is a map of the sky, I believe, at 217 gigahertz. And it's meant to indicate to you where the dust is and where the clean parts of the sky are. On the left is the northern hemisphere, and on the right is the southern hemisphere, and in white is outlined the region that SPIDER will cover. It's also the region that the other experiments that I discussed will be covering. It's a very good part of the sky. And that 8 or 10% is about all of the southern hemisphere that's worth observing, given the level of foregrounds of galactic emission and the rest of it. And there's another roughly 8% of the full sky in the northern hemisphere, which is arguably as clean. But when thinking about the prospects for the future, that 16 to 20% of the full sky is about as much as you could hope to use to probe B-mode emission. And that's challenging just from the point of view not only of statistics, but also of the angular scales that you can reach, that you can hopefully reach in probing B-mode emission. Having only roughly 20% of the full sky represents a real limitation to your ability to effectively measure those large-scale modes. So I don't just plug SPIDER. These are the other experiments for which I have good photos of. There's the Atacama B-mode search, which is in Chile right now, observing. Quiet, which has finished its observations and published last year, holds the current, along with BICEP, holds the current limits for the direct measures of the B-mode power. EVEX flew last year, and then there's BICEP, BICEP 3 or polar, and the Keck array, currently observing now down at South Pole.